Hi everyone, and welcome to the next set of slides. The whole focus on this set of slides is something called homeostasis. Imagine, if you will, that we exist in a world where things are dynamically changing all the time, both within our body internally and outside our body externally. One day it's cold, the next it's warm, maybe it's wet and then it's dry. Inside your body, maybe you have too much water or not enough water. Maybe you need food or you've had too much food. Maybe you are out exercising and you need to make changes in your blood pressure and your heart rate. All these things that can happen to us, all these stressors and internal and external environmental changes do put stress on the body. Now, the human body is set up in such a way that it works best at certain particular widths of default settings. So imagine, if you will, your body wants to have so much water in it. Too much or too little can lead to a problem. Blood sugar, you only want so much blood sugar in your body. Too much or too little, too much meaning diabetes, results in causing problems to the body. If it's very warm outside, if you don't sweat, then you will start to do things to the internal processes due to overheating. That's not good for the body. All of these stresses and influences and the body's reaction against them is called homeostasis. If we look at the word homeostasis from a terminology point of view, homeo means sameness and stasis means standing still. The one problem with this term is homeostasis never stands still. It is always shifting and changing. But ultimately then, what does happen is that homeostasis is balance. It's the body's ability to balance itself within a set parameter. So let's, for example, use blood sugar. So today you ate a chocolate bar. The normal values for blood sugar or glucose levels in the blood is between anywhere from 3 till 6. If you have a chocolate bar under normal circumstances, you might have a bit of a spike to 8 or 9. The body then goes into opening up the cell membranes in such a way that the excess glucose leaves the bloodstream and enters into the cells, thus maintaining a level of 4 to 6. What's important there is that it's not just 4 and it's keeping 4. It's 4 to 6. So anything below 4 leads to a dramatic reaction by the body. Anything above 6 leads the body to another dynamic action in order to maintaining that between 4 and 6. Under normal circumstances, if you did not eat a chocolate bar today, it's likely that if you were not diabetic, you would likely be maintaining a blood level glucose of about 4.4, 4.5, 4.6. But what I want you to take away is that there is a too much and a too little end to the parameters around maintaining homeostasis. So when it is too little, we call it moving left, and when it's too much, we call it moving right. So homeostasis is basically about maintaining balance within the two set parameters. In other words, homeostasis is the condition of equilibrium in the body's internal environment due to the interplay of the body's regulatory processes. So in other words, the internal body is in a constant state of reacting to things that change the body's internal environment one way or the other. And as I stated earlier, going too far one way or the other can result in some major problems to processes within inside the body. So, having said that, because of the fact that things are changing all the time, we can say then that homeostasis is dynamic. It is always shifting the numbers back and forth to maintain that balance within that parameter. It is ceaseless. It is constantly happening. It's happening now where you're sitting in front of the computer. It's happening when you're sleeping at night, when you're exercising, when you're eating. Anything you're doing, all the processes in the body are trying to maintain homeostasis. In other words, it is the range to maintain life. And this range is very narrow, and the body does shift within the range. what you need to take away from this is that moving outside either end of the range can be catastrophic. For example, the pH or acidic level of the human body is about 7.2. If you get down to 7.0 or 7.5, you are on the verge of ceasing to exist. And if you were to go into a hospital setting with your pH values at these numbers, they would be panicked very quickly trying to change those values. So you can see something as small as a 0.2 or a 0.1 can lead to catastrophic changes in the body. So that, thinking of all that, then we can say that all structures, from the smallest cells to the large organ systems, all work towards maintaining homeostasis or balance in the human body. So why do we need a balance? Why do we need these parameters? It has been preset physiologically in your body that each of these parameters for all these things, water levels, blood glucose levels, blood pressure, amount of water in the body, chemical levels of things like calcium, potassium, and so forth, it is set in such a way that as so long as all those things are maintained in the parameters, the body will function at its best, its functional best. So everything will work properly. This means that within this set parameter, there is the optimum center with both a left and right, high and low, generally high to the left and low to the right. Sorry, I contradicted myself there. At either end, the values reach a point where the body will be stressed, and if it moves further, the body may be in crisis to a point where the body may die. So, as I said, the body is always moving towards trying to maintain this homeostasis. You will be taking a course in a couple of semesters called pathology. When you take pathology, you look at a disease state and you discuss the signs and symptoms of that disease. Fundamentally, most of those signs and symptoms you see in the state of disease is the body's reaction to trying to maintain homeostasis within the influence of a disease state. Kind of take that, put it in the back pocket, and remember that for a couple of semesters, because I think it'll come around to help you a little bit later. So we see here, as I said earlier, the normal parameter that can move, for example, blood sugar, as I said, is between 4 and 6 millimoles per liter, and diabetics, they can feel the best at between 8 and 10 millimoles per liter. The reason I have this slide up here, even though I said you can reach a very bad state with higher levels, diabetics actually will maintain a higher than 6 glucose level for extended periods of time. One of the unique things about the human body is that if things stay the same for a long period of time, the body will reset that to being its new parameter. And it won't react as badly. If you, who does not have diabetes, found yourself in a state of 10 millimoles of glucose, you would not feel very well. You would not feel well at all. Whereas someone who's had diabetes for an extended period of time, they may have a high level of glucose, but they're functioning perfectly fine because the body has gotten used to it. But just because the body has not gotten used to it does not mean that if it stays this way for an extended period of times, there won't be catastrophic effects to the physical human body. One thing with diabetics, for example, if they have high glucose levels for extended periods of time, in other words, over years, then things start happening like kidneys functioning stops or starts breaking down. They go into kidney failure or liver failure. The nerves in the peripheral joints, such as the fingers, hands, and feet, will start to die off, known as diabetic naturopathy, and neuropathy. So you may get away for the short term because the body changes the default setting, but in fact, eventually you will pay for it. In other words, then, we can say that homeostasis rules and is the one thing that controls every aspect of the human body. As I said, the body is constantly trying to maintain homeostasis in all aspects. As I said, fluid levels, glucose levels, chemical levels, and so forth. The question then is, how does it do this? As I alluded to earlier when I began the slide set, we have to remember that the human body is constantly bombarded with stimuli that can disrupt or take the body away from balance. It could be an external environment such as temperature. It could be an internal environment. You just ate a big meal and glucose levels are heading up. Stresses can also play a role in changing the balanced environment. And this is a term that you may come across from time to time in the course called psychoneuroimmunological effects. We are now discovering that things such as stress, things aren't going well in life and you're being stressed out, they can also affect control of homeostasis. And there'll be more discussions around that as you move through the program. The thing, though, to take away from this is that the longer the influence towards the imbalance, so the longer someone is not in balance, the more severe is the possibility of a mortal outcome. So this is why when you go to the doctor for your regular checkups and they take blood from you, they look at levels of many, many things. A couple of things come from that. The first is that if one's levels of certain things within blood are too high or too low, it could suggest to the physician that you're in a disease state, and result in some changes that may have to happen, whether it be diet or chemicals or drugs or a surgery or whatever it may be. If we go back to diabetes, they take glucose levels in the blood. If they're exceedingly high, then you may start on a medication that may start to control your blood sugar, or a diet change, or so forth. So how does it be controlled? There are two systems that control homeostasis in the human body: the nervous system and something called the endocrine system. The nervous system is exactly what you're thinking, that messages get sent along nerves in the body and changes are made. Nerve impulses tend to be very quick, so the change happens quickly, but unfortunately those quick changes also tend to dissipate relatively quickly, and that is an issue if that change needs to last over time. So the more common used system in the control of homeostasis is the endocrine system. The endocrine system does not use the nerves, it actually uses chemicals that you may know as hormones. They're much more powerful, having an effect on the body, than nerve impulses. They are slower than nerve impulses, but they last much, much longer. So the majority of changes that occur in the body to maintain homeostasis are done by the endocrine system. So how does this work? Well, it's something called a feedback system. The definition of a feedback system is it's basically a cycle of events in which the status of the body condition is monitored, number one, evaluated, number two, and changed, number three. But this is a cycle, so that doesn't stop. Once it's monitored, evaluated, and changed, it is remonitored and reevaluated and rechanged, on and on and on. As I said earlier in one of the slides, homeostasis is constant and never-ending and always, always changing. So these feedback mechanisms always are working as well. Think of the feedback mechanism as a system by which it's keeping an eye on things and ensuring that the body is introducing chemicals to maintain the balance within the parameters of whatever it is it's looking at. So there are three major components to a feedback system. The first is a receptor. So a receptor is something in the body that gets stimulated by something specific. So for example, let's go back to diabetes. There are receptors that measure blood glucose levels. There is a receptor that measures the pressure in the blood vessels to measure blood pressure. There is a receptor in the body that measures fluid levels. Too much or too little fluid can result in issues. These receptors either send nerve impulses or chemical systems to either the nervous system or the endocrine system to let them know whether things are good, they're within the parameter, or whether things need to be changed because they're either too high or too low. So the receptor sends a message to the control center. It is the control center that has the range of values within the predetermined parameter. Again, let's go back to blood sugar. So the control center is the one that knows that blood sugars need to be between 4 and 6. So it takes the message from the receptor and measures it against the values within the parameter and evaluates it. If it's in the center, things are great. If it's too high, it sends out one chemical or command system. If it's too low, it sends out a different command or chemical to the body. So the receptor the receptor is stimulated, it sends a message to the control center, which then measures it against the parameters, and then, depending upon what the measurement says, sends a command via either nerve impulse or chemical to either increase or decrease to maintain within the parameter. The third and last part of this feedback mechanism is the effector. And the effector is the end organ that will, or tissue, that will release the chemical or impulse to make the changes. So receptor gets the information, sends it to the control center, which measures it against a parameter, sends out a message to the effector that makes the change. Nearly all tissues or organs in the human body can be effectors. So if, again, back to blood sugars get too high, it's measured, it's too high, a message is sent to the pancreas to release a hormone called insulin. Insulin affects cell membranes, which causes glucose to leave the bloodstream and enter into all cells of the body, thus maintaining a proper blood glucose level. So receptor, control center, and effector. You can see here in the next diagram that we see at the top of the slide here that there is a stimulus of some kind that is disrupting the homeostasis. It either increases, goes too high or too low, and the control condition is monitored by the receptor. The receptor sees it's either getting too high or too low, sends a message to the control center that receives it, measures it against the parameter, and then via nerve or chemical signals sends a message back to the effector that brings about a certain change that brings it back to the balanced state, and there is a return to homeostasis, and it is again measured by the receptor and maintaining this whole loop constantly. The receptor is always measuring, the control center is always either making the change one way or the other, and to maintain within the control of this preset parameter. Now, there are two ways that this can happen. There is something called a negative feedback system and a positive feedback system, and we're going to discuss the negative feedback system first. The reason it's called a negative feedback system is because it reverses the change. So if the blood sugar is too high, the negative feedback mechanism will lower the blood sugar. If the blood sugar is too low, the negative feedback system will raise the blood sugar levels back up to the proposed parameter state. When the change starts to occur, so if the feedback mechanism is making the change, the resulting change that occurs in the environment influences the control center to send less signals, therefore resulting in slowing and eventually stopping the changes to stabilize and balance the environment. So we say that the negative feedback system reverses the change, so the change occurs, the negative feedback system slows and eventually stops as the environment returns to balance. But remember, that balance may not stay balanced for very long, and this whole system may start up all over again. So we see here in the diagram again that we have something that disrupts the homeostasis by increasing, in this case, blood pressure. So for some strange reason, your blood pressure is increasing. The receptors in certain blood vessels, called baroreceptors, think of a barometer measuring pressure, the baroreceptors are recognizing that there's an increase in pressure in the bloodstream of the blood. So the baroreceptors will send a message to the brain that says, oh, I'm being told that pressure is increasing in the bloodstream. Now, what has to happen, apologies, sorry about that. Now what has to happen is that the brain will send a message, in this case, to the heart to ask it to increase in heart rate, thus decreasing blood pressure. So repeat again, there is an increase in blood pressure. Baroreceptors in the bloodstream see this, recognize that the blood pressure is increasing, and sends a message to the brain that blood pressure is increasing. The brain, being the control center, then sends nerve impulses to the heart to say, please beat faster, and that increase in faster beat, or in decrease in heart beating, will result in a decrease in blood pressure. I apologize for that. It's a decrease in heart rate, which results in a decrease in blood pressure. So this returns it back to a homeostasis where the pressure returns back to normal. Maybe it gets too low, and a whole other number of steps will occur to bring the blood pressure back up to normal again. The other feedback system is known as a positive feedback system. So whereas the negative feedback system is changing things back, so too high makes it low, too low increases, the positive feedback system strengthens or reinforces the change. In other words, it makes it stronger or faster or quicker. It still is very similar to the negative feedback system because it still uses a receptor and a control center and an effector. The thing that happens with a positive feedback system is it will continue until an outside system eventually shuts it off. And there's a very classic example of a positive feedback system, and that is the birth of a child. So what happens when a child is to be born? Well, there is a contraction of the uterus that forces the baby down into the cervix. As the head travels into the cervix itself will stretch. And within the muscular wall of the cervix, there are receptors that are stretch sensitive. And these receptors in the cervix, as it stretches, it starts to send nerve impulses to the brain. The brain then is stimulated to send a message to increase a hormone called oxytocin. Oxytocin is a hormone that stimulates the muscular wall of the uterus to contract more forcefully. And what's going to happen when that muscular wall contracts? It is going to force the baby's head down even further. With the head traveling down even further, the cervix will stretch even further more, thereby sending even stronger signals to the brain. The stronger signals from the stretch receptors in the cervix will send a stronger message to the brain. The brain will release more oxytocin. The oxytocin will, in fact, actually increase the muscular contraction of the uterus to push the baby further, which further stretches the uterus or the cervix, which further stimulates the receptors, which causes the brain to release even more oxytocin, which causes the uterus to contract even more, and on and on and on until such time that the baby is born. So this cycle continues and continues and continues. The child is born. When the child leaves the cervix is no longer being stretched, and thus it's starting to return back to normal. The stretch receptors calm down, thereby causing the brain to stop or slow down releasing oxytocin. But remember, it's not going to be quite done yet because the placenta needs to be birthed as well. Then after that's all done, the oxytocin then gets to a point where there are no more contractions in the uterus, and the whole positive feedback mechanism stops. The last slide is something to think about, and that is when we're in balance, when the body is in homeostatic balance, everything functions efficiently and to the best of its ability. As soon as we go into a state that is out of balance or into an imbalanced state, it's usually a disease or disorder that's occurring. And what we see, as I said earlier, if we start to look at the symptoms and sites of a disease state, what we're seeing in terms of what's happening in the body, fever, muscle contractions, dizziness, and so on and so forth, is usually a result of the body still trying to move forward to maintain homeostatic parameters in the presence of a disease state. That's the end of the slides. Thank you very much. We'll certainly discuss this a bit in class, and if you have any questions, we'll certainly discuss them after that. Thanks for listening.